you know what? That was going to be part of my lecture.
Okay, we can save it for that then if that works
And then
for
you can ask the, okay, so is there anything else? Anybody? All right. Well, then let's do lecture. So we've already done the exercise with, we've already done the exercise for free body diagrams. So we know how to do free body diagrams, and now basically we're trying to figure out how to use them. So let's see where we are. Go ahead.
Yeah, so I have a question regarding the lab.
Something's really wrong, Aurelio, with your microphone.
Can you hear me?
No, not really. Put it in the chat. Okay. Well, Aurelio gets that ready. Does anyone else have a question? Sure. Adam asks if I can talk about an inertial frame. So an inertial frame of reference is one in which Newton's second law holds. So an example of an inertial frame would be a frame of reference that is motionless with respect to the background of the distant stars. So the Earth is an approximately inertial frame. There are some applications for which the rotation of the Earth has to be taken into consideration, like the Foucault pendulum, which I think we talked about. But basically, you can tell if you're in an inertial frame if there aren't any strange effects. For example, in an elevator, as the elevator moves straight up, if it's accelerating, you feel yourself being pushed down into the floor. And if you were standing on a scale, the scale would read more than what you know your weight is. So what's going on there? There's nothing actually pushing you. So what's happening? What's happening is that the accelerating elevator is a non-inertial frame. A car that's turning in a circle, you feel like you're being pushed into the side of the car if you're a passenger. Again, there's nothing pushing you. So you know that it's a non-inertial frame. We're going to do some simple problems with non-inertial reference frames, and you'll see how to deal with them. The basic idea is you simply step outside the non-inertial frame into the Earth's frame, which we'll assume to be inertial, and then solve the problem that way. And it's very simple. Okay. Aurelio, are you ready? Okay. Okay, so the actual lab manual write-up says that the goal of the lab is to test whether the acceleration of gravity acts like a vector. That's kind of lame. I think the goal of the lab was to measure G. It was a method of measuring G near the Earth's surface. And that's what I would say the goal was. So I wouldn't say that the goal is to compare to gravitational acceleration. I would say that the purpose of the lab was to measure little g. In fact, that's the way I pitched it to you during lab when we did a little bit of lecture ahead of time. Is that okay, Aurelio? Okay, good. All right, well, let's talk about the heavy rope. Now, I want to emphasize something to you. When you're solving one of these mechanics problems, the first thing you want to do is make a free body diagram. That's absolutely the first thing you want to do. If you're in engineering, let's say a mechanical engineer, when you take your statics course, there will be whole lectures on free body diagrams and how to make free body diagrams. So it's a very important subject. What we're doing is kind of a simplified version, but nonetheless, it's important. So Aurelio wrote something more in the chat. The answer is yes. Okay, so let's look at a situation in which instead of an ideal rope, we have a heavy rope. Now I'm going to start by making an ideal rope here. I'm going to attach that to a mass. Then I'm going to attach that to a heavy rope. So that's a heavy rope. And we'll hang another mass off the heavy rope. So this is M1. This is M2. The rope has a mass, which we'll call M sub R for the mass of the rope. There will be a tension here in this ideal rope, but it's just the method by which I hang something to the ceiling. So I've got a real thin little ideal string here, and then I've got a thick, heavy rope here. Think of it that way. Now let's also label the tension here as T at the bottom of the rope, and the tension here, T at the top of the rope. And let's do a free body diagram for each one of these. So for M1, I have M1G acting downward. I have T at the top of the rope acting downward. I have the tension T of the ideal rope acting upward. And I think that is it. Now we're also going to do a free body diagram for the rope itself because the rope is heavy. So what I have is the mass of the rope times G. I also have T at the bottom pulling down, and I have T at the top pulling up. And for mass M2, I have M2G and I have T at the bottom pulling up. Okay, so how do we translate this into equations using Newton's second law? Well, for the first body, we have one equation for each of these. And our equation of constraint is Andreas. What is the equation of constraint here?
Constraints. Apologize, I don't remember seeing that verbiage in the chapter.
Okay, well, that was an idea I introduced to you during lecture. I don't believe the book refers to it as an equation of constraint. Just assume that the things which are the constraints are obvious and you can write down easily. But I wanted to make the idea more formal for you because I want you to think about it. So the equation of constraint here is very simple. None of these bodies are moving. So the accelerations of every one of these bodies, there are three of them, the two masses and the heavy rope, the accelerations of these three are all zero. And you need to know that to write down this second law because F equals ma. So for each of these bodies, the net force must be zero. Okay, so up is positive, down is negative. So for body one, we have T minus M1G minus T at the top equals 0. Now, for the second body, we have T at the top minus the mass of the rope, G, minus T at the bottom equals 0. And for the third equation, for the third body, we have T at the bottom minus M2G equals 0. So it's the equation of constraint that tells me that I can set all of these equal to 0 because A of the rope equals 0, A2 equals 0, and A1 equals 0. Okay, so how do we solve these? Well, I would start at the bottom. Well, first of all, let's make sure we have as many unknowns as we have equations. T is unknown. T at the top is unknown. And T at the bottom is unknown. So I have 3 equations and 3 unknowns. And I'm going to solve them by beginning with the bottom equation. The bottom equation is easy. It says TB equals M2 times G. And that makes perfect sense. You could have written that by inspection just by looking at the picture. G. The tension at the bottom of the row is the only thing holding mass M2 up, so it must be equal to M2G. Since we know that, we can write T at the top is equal to MRG plus T at the bottom, which is M2G. And that also makes sense. Because right here, this tension is due at that point to the weight of the rope and the weight of M2. And now I can figure out what the tension T here is. T equals M1G plus the tension at the top, which is MRG plus M2G, which makes perfect sense. Now, I've solved for the tension at the top and the bottom of the rope. What would be the tension at some other place in the rope? Let's assume that this is a length L. Well, the tension is going to vary linearly. It's going to be 0. I'm sorry, not 0. It's going to be M2G at the bottom, and it's going to be T at the top at the top. So how would I write that linear relation? Well, here, let's write down y equals mx plus b. So the tension in the rope is equal to the slope times the position, and I have to define a coordinate system here. So let's say that y equals 0 at the bottom of the rope and y equals L at the top of the rope. So at y equals 0, the intercept is just going to be t at the bottom, which is m22g. What's the slope going to be? It's going to be t at the top minus t at the bottom divided by L times y, and I used this symbol differently here, didn't I? Just trying to remind you what a straight line looks like, but we're calling this y, plus m2g. Okay. Review the point slope formula or the 2-point formula or whatever you got to do to be able to figure out what a straight line is if you're given, in this case, 2 points. Make sure you understand how to do that because we're going to be doing that a lot in this semester and in subsequent semesters. Okay, so what would be, for example, the tension right in the center of the rope? Well, the tension right in the center of the rope is the average between T top and T bottom. That's obvious since it's a straight line. And any other position on the rope you can determine because you know this. Okay, does everybody understand this particular example? Okay, let me ask you a question. Let's get rid of the masses and let's just hang the rope from the ceiling like it's a bell pull. So you pull on it and you ring a bell somewhere in the servants' quarters or something like that to summon the butler. So I'm sure you have one of these at home, right? It always happens that when such a rope breaks, it breaks at the top of the rope. Why do you think that is? Okay, well, the reason is this. Here's a rope hanging from the ceiling. You pull on it with a force, then the tension at the bottom is going to just equal the force with which you pull it. The tension at the top is going to be the mass of the rope times G plus the force with which you pull it. So the tension increases as you go up the rope at its maximum at the top. So that's why when you ring furiously for the servants, you break the rope at the top, not at the bottom or someplace in between, unless there's a weak point in the rope. But I'm assuming there's no weak point. Okay, someone asked the question, where did we get this from? Well, let's go ahead and graph it. And this is the tension in the rope. Well, when y equals 0, we know the tension in the rope is m2g. So that's clearly going to be our intercept. There's the intercept right there. Now, since it's a straight line, we need to determine the slope. So it's going to go something like this. And this is the tension at the bottom. So this is y equals 0. and this is y equal L. And this value right here is the tension at the top. This was the tension at the bottom. Okay, so what's the slope of the line? Rise over run. Tension at the top minus tension at the bottom over L plus times y, and then you've got the intercept. Okay, does that help? Okay, good. Let's look at the problem of the monkey. So here's the ground. Here's a tree. Here's a limb of a tree. And we're going to say there's no friction for the rope that hangs over the limb. We have a box down here with mass M. It goes over the top of the tree and a monkey climbs up it. Now let's do our free body diagrams. So we've got, for the monkey, we have the mass of the monkey times G, and the tension in the rope is pulling up. Now he's climbing the rope. So when he climbs the rope, he's pulling down on the rope. Therefore, the rope, by Newton's third law, is pushing up on him. That's why I have the tension in the rope acting upwards. Now, let's do a free body diagram for this mass. Well, this is going to be mg, and pushing up is going to be, or pulling up is going to be the tension in the rope, and also pulling up is going to be the normal force of the floor, of the ground. Now, let's put in some constraints. Let's say that the monkey is accelerating up the rope just fast enough to lift the crate barely off the ground and support the crate. That means that the normal force goes to 0 and the acceleration of the crate is 0. So we have the tension minus mg equals 0. Now for the monkey, we have the tension minus the mass of the monkey times g must equal the mass of the monkey times the acceleration a of the monkey. And I have two equations and two unknowns here, the tension in the rope and the acceleration of the monkey. So I'm answering the question, with what acceleration must the monkey be accelerating up the rope in order to support the mass on the other end of the rope? Well, this is trivial to solve. T equals mg. So mg minus the mass of the monkey, g, divided by the mass of the monkey equals the acceleration of the monkey. So let's put some numbers to this, just for grins. Somebody get out their calculator. I don't have mine. So let's let the mass of the crate be 20 kilograms. And let's let the mass of the monkey be 15 kilograms. That's a big fat monkey. All right, what does the acceleration A have to be? Somebody work that out. Oh, actually, you can do it in your head. A is equal to G over 3. So about 3.3, let's say, meters per second squared. That's actually a pretty good acceleration for climbing up a rope. Okay, does anyone have any questions on this particular problem?
Professor, like what?
Yeah.
I'm just curious, like, and I know we haven't gone there. Like, mechanical advantage of like a pulley system wouldn't affect this.
There's no mechanical advantage here. We're going to discuss mechanical advantage shortly. There's no mechanical advantage here because the tension in the monkey side of the rope is the same as the tension on the other side of the rope. Mechanical advantage occurs when the tension that you exert is multiplied where the load is. And a single pulley doesn't do that.
Oh, okay. Oh, you need a block and tackle, right?
You need a block and tackle. Or there's you can do it with a single pulley and with what's called a runner, and I'll show you what that is. Okay, so here's the acceleration of the monkey climbing the rope is G over 3. Okay, let's look at the problem of a non-inertial frame of reference. So let's say we have an elevator, and the elevator has a little scale on it, and you're standing on the scale. That looks like Piglet. Piglet is standing on the scale. Okay. The elevator is accelerating upward with some acceleration A. And my question is, what's the reading on the scale? Well, let's step outside of the elevator and just watch it accelerating and do a free body diagram for Piglet. So what do we have? We have the mass of Piglet times G pulling down, and we have the normal force of the floor, actually the scale, pushing back up on him. And the normal force N will be the reading of the scale. So this doesn't look like we've done anything, but we really have, because the equation is N minus mg equals ma. So that means the normal force is equal to m g plus a, which you would have probably guessed. But to do it formally, excuse me, step outside the elevator, look at the elevator, and write down the free body diagram for the bodies of interest and the equations, because F equals ma is valid for the person standing on the ground here watching the elevator accelerate. What is the equation of constraint here? Jonathan, what's the equation of constraint? Piglet is forced to move in a certain way. How is he forced to move?
I mean, wouldn't it just be like, it'd be that she's moving, so it'd be like the acceleration, wouldn't it?
He has to accelerate at the same rate as the elevator because he's standing in the elevator and the bottom of the elevator is accelerating upward with A. He must be accelerating upward with A as well. Now, I'm assuming that the acceleration isn't so great that he's crushed. So he's just standing there on the scale. So the equation of constraint is that the piglet is moving with acceleration a, the acceleration of the elevator. Let's say now we do something different. Let's say now the acceleration is downward and equal to a. Well, we still have the same exact free body diagram. So we have n minus mg is equal to ma, but a is negative, so I'm going to let a be a positive number and put the negative sign right here. So it's accelerating downward with acceleration a. Well, now the normal force is less than piglet's weight because it's equal to mg minus a, because it's moving downward. Okay. Does anybody have any questions so far?
I don't have a question, but when you mentioned that we had a lecture previously, I don't recall us having one about constraints or free body diagrams, because we just had the test Monday and then you let us go.
Oh my gosh.
It's making reasonable sense right now, but I don't want
I'm
to
giving
interrupt
I'm
you.
giving you Thursday's lecture. The other class is one class ahead of you. So we got to go back and begin chapter 4, don't we?
I believe so.
Yes, you believe correctly. Oh God. Okay, I'm sorry. Oh, I'm sorry. Okay.
I was feeling so lost when you called on me. I was like, shit.
I'm really sorry. Okay. So that was kind of an interesting preview. So what I just gave you was kind of a nice preview of coming attractions. So let's start at the beginning and do this right. So we are going to study dynamics. And what is dynamics? We're beginning our study of dynamics. Well, kinematics was the study of the geometry of the motion. So accelerations, velocities, positions, but without any reference to what gave rise to the accelerations. And it turns out that accelerations are caused by forces. So we are going to include forces in our theory. All right, so let's begin with Newton's laws of motion. Newton's first law of motion. A body with constant velocity will continue to have constant velocity unless acted on by a force. But we don't yet really know what force is. So for now, consider force to be the plain English meaning. I push on you, I'm pushing on you with some force. Okay. So another way to state this is that a body traveling in a straight line will continue in a straight line with constant speed until it's acted on by a force. This is completely different from the Aristotelian view. Aristotle believed that if you stopped pushing on something, it would come to rest. So how did he explain an arrow flying through the air? What's pushing it? Well, people before Newton invented all kinds of silly theories about how the air behind is pushing it forward and the air in front is not pushing back, and all kinds of nonsense. But the correct way to think of it is that if there's no forces acting, a body's just going to continue in the motion that it has. Now, the second law is actually the definition of force, the famous F equals ma. So if I know the mass of an object and I know what its acceleration is, then I know what the force is. This equation is actually a vector equation. So I should put a little vector sign over the F and the A. And M, of course, is a scalar. Now, what are the units of force? The units of force are mass times acceleration. So that's a kilogram meter per second squared. And we call that, in honor of Sir Isaac, we call that a Newton. We usually just use the symbol capital N for it. So what is 1 Newton? It is the force necessary to accelerate a 1 kilogram mass at 1 meter per second squared. That would be 1 Newton. It turns out that there are about 2.5 newtons to the pound. So pound is a force, not a mass in the English system. Does anyone know what the mass in the English system is? What's the unit of mass in the English system? It's called a slug. So it is improper when doing physics in the English system to use pound as if it is a mass. You have to use the slug as a mass, and the slug is an amount of mass that would weigh 32 pounds in the Earth's gravitational field near the surface. Okay, but we're not going to care about that. We only care about MKS. So the MKS unit of force is the Newton. Now the third law sometimes causes confusion for the students. The third law says for every action, and action is an old-fashioned word for force, for every action there is an opposite and equal reaction. Now, what do I mean by equal? What I mean is equal in magnitude. Since it's opposite in direction, the vectors aren't equal. The two vectors have the same magnitude. So if I push on you with a force F, you are, by Newton's third law, pushing back on me with that same force F. This is kind of confusing sometimes. Let's say we have a horse and the horse is pulling a cart. And let's say the horse is running and causing the cart to accelerate. What is making the cart accelerate? The force that the horse is exerting on it. But by Newton's third law, the cart exerts an equal but opposite force on the horse. So it is a common misconception that those two forces cancel and that therefore the cart can't move. Okay, this is erroneous. Who would like to think about it? Well, think about it, and then someone volunteer and tell me what's wrong with that reasoning.
Let's say that the cart was heavy, it would make the horse slow down, but not necessarily stop.
No, that's not the answer. The force on the cart due to the horse is exactly the same thing, exactly the same magnitude as the force on the horse due to the cart. Did I say that right? I think I did. Force on the cart is the same as the force on the horse. If I have a little old lady with a cane and an NFL linebacker, and they run into each other, the force that the little old lady exerts on the linebacker is identical to the force exerted by the linebacker on the little old lady.
Because then there'd be no, by that logic, there'd be no movement.
So if those two cancel, then how do you ever accelerate anything? So why is it wrong to say that they cancel?
Because of inertia.
No. Anybody? Okay. This is a very important point, and I want you to make sure you understand it. The action-reaction pair do not cancel because they act on different bodies. We write down in a free body diagram, let's say all the forces acting on the cart. And we write down all the forces acting on the horse. Okay? They don't cancel because they're acting on different things. The forces only cancel when they act on the same body. Okay, so let me give you an example.
Professor,
Yes,
can I ask you a question on that? Like,
yes.
and I think you might be explaining it right now, but like, I'm just saying, like, say, like, I had an exact replica of myself, and one was standing still, and the other one was like tackled the other one, like the linebacker situation.
Okay.
Like, would they not consider the same body because, like, one it has acceleration, or one has velocity, and the other one does not?
Well, they're not the same body. One of them is the person you tackle, and the other one is you.
Oh, okay, so it's like a sum. Okay, got it.
Now, what about this question? Why does the little old lady get hurt and the linebacker doesn't? Because the
because of their
forces on them
mass?
are the same.
Oh.
But someone said it, and I interrupted. Go ahead and say
I was
it
going
again.
to say because of their mass.
The masses are different. That's right. So the same force acts on the little old lady. Her mass is less. Her acceleration is greater. The linebacker has the same force. His mass is greater. Therefore, his acceleration is less. So the effect on the two bodies is not the same, but the forces, one on the other, are an action-reaction pair, and those forces are the same magnitude. Okay, now here's a floor, here's a table, and here's a book sitting on the table. So I'll call this M, mass of the book. Okay, Sophia, explain to me how this situation of the book, so talk about the book, not the table. How does this situation of the book demonstrate Newton's first law?
Not sure.
Well, the first law says that the body with constant velocity continues to have constant velocity unless acted on by a force. What's the velocity of the book? It's sitting there motionless. What's its velocity? The question was for you, Sophia.
She typed 0 in the chat.
Oh, she said 0 in the chat. Okay. That's correct. Now, is there a net force acting on the book? No, there's no net force acting on the book. So it continues to have 0 velocity unless I put some additional force somewhere on it. So, Christopher, explain to me how this demonstrates Newton's second law.
since its acceleration is 0, whether its mass is any number, its force would be 0?
The net force has to be 0. Its acceleration is 0, therefore the net force on it is 0. And that's exactly the case for the book, right? Now, here's the tricky one. Benjamin, explain to me how this situation demonstrates Newton's third law. You'll have to talk about both the table and the book.
I would say the book is acting on the table and the table is pushing back on the book.
There you go. There you go. For the book, gravity is pushing down on the book or pulling down on the book. The table is pushing up. I'm going to call that the force of the table. Now, what about the table? Well, the force of the table on the book is the same as the book on the table. So Ft acts downward, as does the mass of the table times g. And what's pushing upward? The force of the floor on the table, pushing upward. Okay, so these two forces right here are equal in magnitude, and they constitute an action-reaction pair. So action-reaction pairs do not cancel each other because they act on different bodies. So I could write down the equations of motion here for these two bodies and solve them. And we'll do that later. We'll see how to do that later. All right, now I actually did an example here for you of a free body diagram. Free body diagrams are extremely important. As I said, in mechanical engineering, you're going to spend a lot of time on free body diagrams. They have whole workshops on doing free body diagrams. And the idea of a free body diagram is this. Put down a little dot in space to represent the body, and then put a coordinate system on it if you want, and indicate with arrows all the forces. So let's do the book again. The mass of the book times g is the gravitational force pulling down. The force of the table is pushing up. That's my free body diagram. All right. Let's talk about kinds of forces. And then we're going to do an exercise with free body diagrams. So let's talk about kinds of forces. So there are 4 basic forces in nature. Aman, can you tell me one of them? There are 4 basic forces in nature. Just give me one of them. Pick any one you want. All right. Joshua? Okay. Lewis?
Sorry, what was that?
There are 4 basic forces in nature. Go ahead and name one of them. Pick any one you want.
Acceleration.
No. No, there are 4 basic forces in nature. 4 fundamental forces.
Is one of them gravity?
One of them is gravity. Okay, somebody name me another one.
Friction force.
Nope, that's not a fundamental force.
Oh,
Would one be like the magnetism of the poles?
Okay, someone said contact forces, and that's wrong. You're almost right. Electromagnetic force. So electricity and magnetism are really 2 sides of the same coin. In fact, magnetism is a special effect of charges in motion. So it's related to electricity. They're unified as the electromagnetic force. So that's one of the 4 fundamental forces in nature. Who's had chemistry? Someone who's had chemistry, tell me another one.
It's not weak and strong nuclear.
There you go. Those are the other 2. And weak nuclear. Okay. So gravity, we're going to study in detail and through the universal law of gravitation. But right now, near the Earth's surface, since the acceleration for any body is g, the gravitational force on any body near the Earth's surface is simply going to be mg. So for now, we're going to model gravity as the force of gravity equals mg. And you have to put a sign in there, positive or negative, depending on how you define up and down as positive or negative. We'll take down to be negative most of the time. Okay. Gravity was the first of the 4 forces to be identified and at least partially understood through Newton's universal law of gravitation. Now, the electromagnetic force is going to be the subject of all next semester. And you know the basic phenomena is that like charges repel and unlike charges attract. So consider that to be the basic phenomenon of electromagnetic forces. The strong nuclear force holds the nucleus together, and the weak nuclear force holds the neutron together. And that's it. There's only 4 of them, as far as we know. And there are supposedly reasons to believe there are only 4. Now, let's classify forces for the purpose of this class so that we can talk about them. The first force is gravity. Now that's one of the fundamental forces, and we're modeling it as just mg. The second kind of force we're going to classify are normal forces. Now, I don't mean normal as in ordinary or not fancy. I mean normal as in right angles. So the normal forces always act at right angles to the surface of contact. So in this example, the table pushing up on, oh, didn't mean to do that. The table pushing up on the book is a normal force on the book because it's at right angles to the surface. And the force of the book pushing down on the table is also a normal force. It's at right angles to the table. Okay. Now, a third category of forces are tension forces. The tension forces are the forces that are in ropes and strings, and the direction of the force is along the direction of the string. And we're going to model the tension forces in strings, in ideal strings, and we're going to only occasionally look at strings that aren't ideal. We're going to model that tension as being the same at every point in the string. Now, for a heavy string in the Earth's gravitational field, the tension is not the same everywhere, is it? But for ideal strings, it is. What makes an ideal string? An ideal string has no mass, and it is perfectly rigid. It does not stretch. However, we will consider it not to be rigid in compression. So you've heard the phrase, go push on a rope. Okay, well, what happens when you push on a rope? The rope just collapses. Okay, so we're going to consider it to be perfectly rigid in tension, but we're not going to put ropes in compression because it doesn't make any sense to do that. We're going to pull down on them. We're not going to press on them. Okay, and a fourth category is friction. Now, friction is an interesting animal. We're not going to discuss it in detail because we don't have a model yet for it, but we're going to model friction in a simple way in the next chapter. Friction acts in this way. Normal forces always act perpendicular to the surface of contact. So here's the floor, here's the mass M. The normal force on M acts normal to the surface, pushes up on M. Let's say that M is sliding in that direction. The friction force is parallel to the plane of contact. So the friction force is this way. So friction forces are shearing forces. Shear means nothing but in the plane of contact. And normal means perpendicular to the plane of contact. Now, what direction does friction act? Well, friction always acts to oppose the direction of, and I'm going to write incipient motion. So if the body is moving, friction always acts to oppose the motion. Let's say that I pull on this block with a tension T, but the block isn't actually moving because the tension is not great enough to overcome the frictional force. If it's not moving, how do I decide the direction of the frictional force? Well, the frictional force opposes the incipient motion. The incipient motion is the motion that would occur if friction were not present. So if I have no friction, my block is going to move that way. Therefore, friction opposes that motion. We call that the incipient motion because it's not actually moving. Yes, air resistance is considered a kind of friction, but it's going to be modeled differently than the friction between solid surfaces, because in order to determine the friction due to air, you have to solve the fluid mechanical problem of the body moving through the air. And that's not usually easy. But our model will apply, to macroscopic objects that are rubbing against one another. And we have yet one more category of forces. The fifth one is applied forces. What do I mean by applied forces? It's just a name, and it means a force that I apply usually with my hand. So a problem in mastering physics might say, you attach a rope to a block and you apply a force of 10 newtons to the rope in the direction to the right. That 10 newtons to the right is an applied force. So you're applying it somehow with your body, with your hands usually. Now, this force, gravity, is fundamental. It's one of the 4 fundamental forces. All of these other things are not fundamental forces. We give them names because these kinds of forces occur in mechanics problems, and we want to be able to talk about them. So we give them names. Applied force, friction, tension, compression. I forgot about compression. We're not going to usually worry about it. But what is their fundamental nature? Does anyone know what the fundamental nature of those forces is? It's got to be one of the 4. It's not gravity, so it's got to be one of the others. Anybody have a guess? Okay. All of these forces are electromagnetic in nature. What do I mean by that? I press my hand down on the table. Why does the table resist my pushing on it? Because the electrons in the molecules in my hand are repelled by the electrons in the molecules of the desktop. So all of these things where bodies come into contact and exert forces on one another, the nature of the force is actually electromagnetic. We won't worry about that. We'll just assume that we can measure it or calculate it. Not from first principles, not from electromagnetics, but from the first principles of mechanics. Okay, so that's all about forces. Now I want to make a comment here about forces. In Newtonian dynamics, we determine the motion of the bodies due to the forces on them. But Newton's laws are true no matter what the nature of the force. So Newton's laws apply to all of these forces. So one program of physics is to determine what is the motion of a body when it's acted on by forces. And another program of physics is to understand what is the nature of the force. In gravity, we know that the nature of the force from the universal law is such that a constant times mass 1 times mass 2 divided by r squared, where r is the distance between the masses, that's the magnitude of the gravitational attraction between them. And for electricity, the electrostatic force is some constant k times charge 1 times charge 2 divided by the distance squared between them. Now, the strong and the weak nuclear forces behave in an entirely different manner. But the electrostatic force and the gravitational force are formally identical. They look exactly the same, don't they? It's the same equation. Well, you're going to find out when you study electromagnetism that there are a lot of similarities here between these two. But we're going to study this law later on this semester. Okay, so right now, we're not concerned with the nature of the forces. We have a model for gravity, and the other forces, call them contact forces if you like, to which we give these different names. We know they're electromagnetic in nature, but we don't care. That's transparent to us. All we know is that bodies can collide and exert forces on one another. Or I can push on something or pull on something if I want. Okay. Let's see. Oh, you know, there are some restrictions on Newtonian mechanics. And those restrictions are this. So this is the restrictions on Newtonian mechanics. First restriction is that we have to be in an inertial reference frame. So Newton's laws of motion are not true in a non-inertial frame. And how do we know that we're in a non-inertial frame? We see effects that don't make any sense. We feel forces when there's nothing pushing on us, is the easiest way to say it. So how do I deal with a non-inertial frame? I have to formulate the problem in an inertial reference frame, and then Newton's laws apply. The other restriction is that we are going to talk about speeds that are much less than c, the speed of light. Why is that? Well, in Physics 223, you'll learn that the speed of light is a limiting speed in the universe. And an object that is massive can never be accelerated in finite time or with finite energy to the speed c. It always must be less. That puts kind of a twist on your dynamics. F equals ma is still true, but some of the definitions change, and the interplay between relative velocities of and positions of bodies moving relative to one another are different from what we're going to study. By the way, what we're studying is called Galilean relativity, and you already know Galilean relativity. In chapter 3, we did relative motion. That's Galilean relativity. That's no longer true in special relativity. But the basic idea, F equals ma, things like that are still true. We're just not going to deal with those yet. So we're always going to be at much less c. And what is c? C is 3 times 10 to the 8 meters per second. And relativistic effects become important at about 1/7 of that. So 1/7, 3 times 10 to the 8 meters per second is really a huge speed. So we're not going to ever see those in that one. There are 2 more constraints. Bodies are large, and energies are large. We don't yet know what energy is. We'll learn that. But if we are talking about bodies that are large and energies that are large, we are in the realm of Newtonian dynamics. If we talk about bodies that are small, and what do I mean by small? I don't mean a dust particle. A dust particle is a macroscopic object. You can see it. What I mean by small is atoms and molecules. And when I say energies are large, I mean the kinds of energies that macroscopic bodies have. A bullet, a golf ball, whatever. When I'm talking about energies that are small, I mean something like the energy of an electron as it orbits the nucleus of an atom. Okay. When I'm in the macroscopic regime, I'm in the regime of Newtonian mechanics. If I'm in the microscopic regime, and I don't mean a microscope, because things you can see with a microscope are big. In the microscopic regime, by which I mean atoms and molecules, that kind of size, I'm in the realm of somebody tell me what kind of mechanics am I dealing with there?
Quantum?
Quantum mechanics, exactly. And quantum mechanics is a violent recasting of Newtonian dynamics. However, I want to make sure you understand something. What you are learning is not wrong. What you learn in class is not wrong. I don't have to go back and say to you at any point, oh, by the way, I told you a lie back in week 3 is this. No. Everything you're learning is correct, given the regime of applicability. And what is the regime of applicability in Newtonian mechanics? It's these things right here. Now, what if you have a speed that is comparable to the speed of light? Well, special relativity comes into play. What if you try to use special relativity to analyze a problem that is in the regime of Newtonian dynamics? What do you think you should get? What kind of answer would you get? Why don't you, Shifa, you answer that for me. I use special relativity to analyze a situation in which the speeds are low. What kind of answer am I going to get? Okay, Matthew?
Can you repeat the question really?
Sorry. I use special relativity, which I need to use in order to analyze situations in which speeds are very large. But I use special relativity and I analyze a situation in which the speed is very slow. What kind of answer am I going to get? Is it going to be wrong or is it going to be right?
I'd assume it'd be wrong.
Nope. No, it's going to be right. It's going to be right. But it will be the same answer that I get using Newtonian dynamics. So in the regime in which speeds are large, I have to use special relativity to get the right answers. But in the regime in which speeds are low, the answers of special relativity are the same as the answers of Newtonian dynamics. So Newtonian dynamics isn't wrong. It is the limiting case of special relativity when my speeds are very low compared to the speed of light. Same thing with quantum mechanics. If I try to analyze the orbit of the Earth around the Sun using quantum mechanics principles, I better get the same answer as Newtonian dynamics, right? Otherwise, quantum mechanics has got to be wrong. So Newtonian dynamics is also the limit of quantum mechanics when bodies are large and energies are large. So it's not wrong. It's just the limiting case of a more complete theory, which you don't need when in the regime when Newtonian dynamics applies. But if you used the more complicated theory, you'd still get the same answer as Newtonian dynamics. Okay, does everybody get that? That what I just explained to you has a name in physics. It's called the correspondence principle. It was enumerated by Niels Bohr. And basically he says, in the limit, as bodies are large and energies are large, quantum mechanics gives the same answer as classical physics. And if it doesn't, you've done something wrong. So it's a test. It's actually a test of a quantum mechanical theory.
Professor?
Yes.
I'm just trying to like clarify this and like think about it. Like, so like it's kind of like the transfer or like the shift of this like would maybe be like how you're talking about like jerk, snap, crackle, and pop. Like, for example, like something was in free fall down to earth. Would it be like the like derivatives of acceleration as like gravity increases or like the air gets thicker? Is that kind of like what I'm to understand? Like that shifting from the quantum into the
No, not at all. All of those things you described are analyzable using classical physics because everything's macroscopic. Air friction It's macroscopic. I mean, the air molecules are microscopic, but we don't consider them individually. We consider the air to be a continuum, and we model it with classical mechanics. So all of those
Okay.
things that you described are entirely within the realm of Newtonian physics. Now, talk about an electron going around a proton for a hydrogen atom. You're not in the Newtonian regime anymore.
Okay, so
But
basically at this point,
interesting,
like we can almost just forget everything about, for now, we just forget everything about quantum, and we're like, that just doesn't even matter. Like we're just focusing on what we were focused on in the class.
well, yes, I don't want you to go and get a lobotomy and remove whatever you know about something else, but we're going to concentrate on classical mechanics, Newtonian mechanics, yes. Yeah, but like I said, don't go get a lobotomy or anything if you happen to know some quantum mechanics. You know, that's okay. You'll see it again in Physics 223. Okay. Interestingly, one of the fundamental equations of quantum mechanics, the Schrodinger equation, is really nothing but conservation of energy written in a quantum mechanical way. So many of the concepts of classical physics carry over. Energy is conserved, momentum is conserved. You know, these things that we're going to learn are still true on the quantum mechanical level, but some other things are not. Okay, so free body diagrams. If you go onto Canvas, you will find a handout that is called free body diagrams, I think. I'm going to bring it up here. Oh, I'm looking at the wrong one. Jeez. Okay. Now, under handouts, you'll find this. It is free body diagrams. And it looks like this. Now, I've already done the block sitting motionless on a table. But let's redo it just to remind you how this works. So I put a little dot there in the middle of the paper to simulate this mass M. And what are all the forces that are acting on it? mg and the normal force of the table. So I'll just call it N. You can call it F table if you want. I don't care what you call it. You can call things anything you want. And that's it. That's all that's happening to the block. Now, some of these problems have more than one object that you have to do a free body diagram for. Now, I also ask you to determine the equation or equations of constraint. If you don't know how to write it as an equation, then say it in words. But for this particular problem, the equation of constraint on the block is that the block's not moving. So the acceleration of the block is equal to 0. That's an equation of constraint. There may be more complicated and more interesting equations of constraint for some of the other problems, but think about them. Now, equation of constraint is not a concept in your book. In your book, they'll just say, well, write down the equation and it's obvious A must equal 0, so write 0 in the equation. But I want you to think a little bit about what's happening physically and think about there's something constraining the motion somehow. And that needs to be included in your formulation of the problem. So for this exercise, we're not going to solve the problems. We're not even going to set up the equations. All we're going to do is do free body diagrams and talk about the constraints. So here it is. I would download it and print it out so that you can make notes on it. But what I'm going to do is we're going to go through all of these, and I'm going to call on everyone in the class to answer a question about these. And there's enough that everybody will have a chance. And that will be graded. I will give you credit for this exercise or not, depending upon whether or not you respond. I'm not going to ding you if you respond incorrectly, but you've got to try to get credit. Okay, does everyone understand? So I'm going to let you chew on that for a while I take a break. So you can take a break for yourself and print this out and sit down and look at it and have a drink or whatever you want to do. And let's meet again at 3:20. Let's say half an hour, 3:25. So in half an hour, we'll reconvene and discuss free body diagrams. Okay, anybody have any questions, comments, concerns? All right, then I'll see you in half an hour.